Welcome to our lesson on kinematics, the branch of physics that studies the motion of objects without delving into the forces causing it, though we'll touch on those concepts briefly. Today, we'll analyze a classic physics problem straight from educational materials. A car accelerating from rest at time 0, then decelerating to a complete stop at total time t. Imagine a car that starts from rest and accelerates at a constant rate, denoted as alpha, for a duration up to time t1, thereby reaching its maximum velocity. After reaching its peak speed at t1, the car then decelerates at a constant rate, denoted as beta, over the remaining time until it comes to a complete stop at total time t. Our primary goal in this example is to calculate two key quantities: the maximum velocity vi that the car achieves during its motion and the total distance it travels throughout this entire acceleration and deceleration process. The most effective and intuitive way to visualize and analyze this type of motion is by using a velocity time graph as presented in standard kinematics worksheets. This velocity time graph plots velocity on the vertical axis and time on the horizontal axis, resulting in a distinctive triangular shape that represents the entire motion profile. The initial acceleration phase of the motion, during which the velocity increases linearly from 0, is clearly represented by the first rising segment of this graph. In this phase, the constant acceleration alpha is precisely defined as the change in velocity v divided by the time interval t1, so alpha equals v over t1. Following that, the deceleration phase, where the velocity decreases linearly back to 0, is represented by the second descending segment of the graph. The constant retardation or deceleration beta is equal to the maximum velocity v divided by the time taken for deceleration, which is the interval from t1 to total t or t minus t1. By carefully combining these two fundamental equations from the acceleration and deceleration phases, we can derive a useful expression for the maximum velocity IV solely in terms of alpha, beta, and the total timed. This step-by-step derivation ultimately leads us to the elegant formula for maximum velocity. V equals the product of alpha and beta times t, all divided by the sum of alpha and beta. Now, to find the total distance traveled by the car, we note that in a velocity time graph, this distance corresponds directly to the area under the velocity curve from t to t. Since the graph forms a perfect triangle with base equal to total time t and height equal to maximum velocity v, the area is straightforwardly calculated as 1/2 times base times height. Thus, by substituting the total time t as the base length and the maximum velocity v as the height, the total distance simplifies to 1/2 times t times v. Finally, by substituting the derived expression for v that we obtained earlier into this area formula, we arrive at the complete and comprehensive formula for the total distance traveled during the motion. Mastering these kinematics concepts, as illustrated in resources like Topper's learning worksheets, equips us to predict and analyze the motion of objects accurately, forming a fundamental skill in physics education.